We just finished talking about chapter one, right? And chapter one was about measuring things and significant figures and uncertainty of measurement and stuff like that. So that stuff is done for that chapter. So now we're going to go into chapter two. In chapter two, we'll be talking about for the next 3 days. Chapter two is about atoms, molecules, and ions, right? Which you actually get a lot deeper into molecules and ions in Gen Chem 2 when you're going through the chapter that's on chemical bonding. But the on chemical bonding, but we'll get a very cursory look at what things mean here in this lecture today. Let me make sure I got my pencil working. Oh, by the way, I finally got my calculator thing working, which really sucks because like we don't even actually need the calculator today. But I just wanted to show you that this does actually work, and so see, look at that, it actually works now. Isn't that amazing? Like how long did it take me to get it to work? Who knows? But I finally got the calculator screen working. Unbelievable. The things I go through for you guys just to get a calculator on the screen, which is not even the right calculator. Where's the right calculator at? Oh, there it is. Here we go. I forgot we were using the calculator yesterday in my forensics class to determine the direction of blood spatter, right? See, you guys should have taken that class. You should have taken my forensics class. Then we could have been talking about blood instead of talking about atoms. Both are fun for me, but I would imagine that blood spatters are more fun for most people than atoms are. So, but yes, let's get started. Let's get started here, okay? I'm trying to get it so I can see both the chat window and the PowerPoint controller at the same time. There we go. Come on, you can do it, guys. You can do it. You can do it, teams. Okay, there we go. All right, so let's start out by talking about the atomic theory of matter. So in the atomic theory of matter, before I get started, let me actually do this too. Oopsies. Make sure I can write. There we go. So let's talk about the atomic theory of matter, right? So there's this Greek philosopher, right? Some of them like Democritus believed that there was a smallest particle, and that smallest particle was known as the atomos. The atmos. Oh, in fact, right? If you have gas at your house, right? If you have gas at your house for your heat and stuff, right? One of the companies that provides it, which provides my gas, is named Atmos, right? And they were not very helpful last year during the deep freeze because they shut off my gas, right? I mean, granted, I called them and told them that it was low pressure, but still, no, they still shut it down. So I was very cold for a few days there because of the Atmos. But this is a different Atmos, right? This Atmos is the precursor to the word atoms, right? And so in the 1800s, the early 1800s, this guy named John Dalton, which is a famous guy in chemistry, super famous guy. The Dalton is also what we use for molecular weight as well. And so John Dalton came up with his atomic theory of matter, right? So it's called the Dalton's atomic theory of matter, right? And it's based on three different laws, right? It's based on three different laws. It's the law of constant composition, the law of conservation of mass, and then the law of multiple proportions. And we'll go through each of these in a second, right? We'll go through each one of these in a second, but just make sure that these three laws are what comprise, right? Comprise the these three laws are what help determine the atomic theory of matter, okay? And so your first question for today, right here, is there, and let me actually take it up calculator. Go ahead and scan that barcode there or that QR code there for attendance today. And for those of you who need the link to do attendance, I will open that up for you, send you a link for attendance. There we go. That was Dalton, okay? So which of the following, which is not a law that atomic theory was based on, right? Let me copy the link over here. Everybody go ahead and scan in and do your thing, do your two-factor authentication multiple times today for attendance. Here's the link, right? So which law is not one of the laws that the atomic theory was based on? Okay, which law was not one of the laws that atomic theory was based on? Was it the law of constant composition, the law of conservation of mass, the law of gravitation, or the law of multiple proportions. Okay? And for some reason, I'm not getting any responses. Why am I not getting any responses? Did I give you the wrong form? The question is different. I gave you the wrong form. Sorry. Let me go back and do this again. Hold on 1 second here. Oh, dang it. What happened there? That's the wrong one. Where's the correct one at? That's so weird. I don't even have that question anymore in here. That's super weird. It's okay, Bella. I'm having some technical issues anyway. So, you know what? Let's skip this question because I don't know why, but that question's not even on my list of questions. Where's it at? Oh, wait, there it is right there. There we go. I found it. I apologize. Let me actually put in the correct link here. I went to the wrong link. There you go. There's the link. There's the correct link. I put in the wrong link in the chat if you needed that. Okay. But I got 3 people have answered already for this one. 4 people have answered. Well, a lot of you must be on your phone. You were waiting for that link with bated breath, I guess. Oh, that reminds me. Attendance was due yesterday or on Monday, and I still haven't done attendance yet. So I need to make sure that I send in your attendance so that everybody knows, or so that the registrar knows that you guys have actually been coming to class, right? So right after class, I'll submit attendance to the registrar's office. All right, I got 8 people responded so far there. 8 people so far have responded. 10 people. Good, good. That's how you. What do you mean? That's how you get paid? Raymond, what do you mean? That's how you get paid? Like the attendance is how you get paid? Am I keeping you from getting a paycheck? I wish this was like iMessage so that I could see like the dot 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 thing if someone was typing in. But I guess if multiple people are typing in, it would get very confusing. Oh, your benefits matter based on the based on the attendance. I got you. FAFSA won't give if you weren't there. Oh, that's true. That's actually the reason why we have to take attendance now. Back in the day when I was in college, right? Um, I know my VA benefits and financial aid depends on attendance. Absolutely. It turns out that my the reason why we actually have to take attendance now is because of that. Because there were people that were getting financial aid loans, right? And then what would happen is they get the loan for the class, and they would pocket the extra money, and then they would stop coming to class. And so what happens now is that uh, if you do that, right, and it shows that you haven't been attending class, and then you took the loan money, you have to pay it back immediately. And so that's the reason why. So it's a Department of Education thing now that you have to actually take attendance, so that they can make sure that people who are taking student loans and VA benefits are actually like for education are actually going to class, right? Crazy stuff. That being said, only 11 people have actually done attendance. This is important, people. Come on, do your attendance. We have 16 people in the class. Where's everybody? There's 12. So I'm still waiting for like 2 more people here. Okay, that's probably enough. I'll go ahead and keep on getting in your answers because attendance is important. Okay. So, oopsies, didn't mean to do that. There we go. What was the question here? Was what was the law? What is which is not the law? A law that the atomic theory was based on. Most of you, 8 of you, said C, right? And C is the law of gravitation. That is absolutely true. Good job there. The law of gravitation has nothing to do with the law of matter. The law of gravitation was one of Newton's laws, right? And yeah, Newton is definitely not Dalton. Okay, so good job there. Good job there. There's still 2 people left that have not done their, or 1 person rather, that has not done their attendance. So make sure you get your attendance in. It is important. Okay. All right, so let's keep on moving forward then, okay? All right, so let's talk about each one, right? We've actually talked about the law of constant composition already when we were talking about it in chapter 1, right? But just as a review, this law, the compounds have definite composition, right? And what that means is that the relative number of atoms of each element in the compound is the same in any sample, right? And so if you have an element of oxygen on one side and you have an element of oxygen on the other side, they're both going to be the same atoms of oxygen, right? Which again, this is one of those things I told you before, where it's like, it seems pretty obvious today, but back then it wasn't very obvious at all. And so you think to yourself, man, I really wish I could have come up with that because then I would have laws named after me. So this law was actually discovered by a guy named Joseph Prost, right here. Joseph Prost. Oopsies. Joseph Prost, okay? And this law was one of the laws in which Dalton's atomic theory was based on, right? So Dalton drew on this law, Joseph Prost's law, right, to make his atomic theory, okay? So the next one is the law of conservation of mass, okay? And here, the law of conservation of mass says that the total mass of a substance present at the end of a chemical process is the same as it is present before the chemical process took place, right? And so a short way of saying this law is matter can not be created or destroyed. In a chemical process, right? Which is actually very similar to one of the laws of thermodynamics, which is energy cannot be created or destroyed, right? It just changes form, okay? And so that's the same thing with matter, right? Matter cannot be changed, cannot be created or destroyed. It only changes form, okay? And so this law was actually discovered by a guy named Antoine Lavoisier, right here, which I'm trying to do my Duolingo thing so I can learn French at the same time. Not at the same time, but learn French right now, or relearn French. My grandpa spoke French, and so I'm trying to relearn it so that I can. He taught me French too, but for some reason I didn't have anyone to practice with, and ever since he died, I really had nobody to practice with. So I'm trying to reconnect with my French roots by doing the Duolingo thing and relearning French. So one of those things is learning how to say French names like Antoine Lavoisier. Maybe that's how you say it. Lavoisier. Lavoisier. Right? That's like when Hermione was teaching Ron how to do the levitation charm, which was I can't remember what it is now. What is a levitation charm? Whatever. If you remember what the charm is for levitation, put it into the chat for me, because I can't remember. Oh yeah. It is Wingardium Leviosa. Not Leviosa. Leviosa. No, it's the other way around. It's Leviosa, not Leviosa. Oh yes, Wingardium Leviosa. Right? That's French. That sounds French. Someone, Deepka just asked, is my attendance done or not? I don't know. I can't check right now. Did you do your attendance? You need to scan the QR code. Let me see. Oh yes. Okay. Now there's 13 people. Good. Very good. Everybody's done their attendance. All right. And Just know that if you scan the QR code and put in your username and password from Texas Wesleyan and answer the question, it will do your attendance for you. Okay. All right. So let's keep going here. All right. So this one was the law of conservation of mass. Right, was discovered by Antoine Lavoisier. Lavoisier, and then we have the next one, which is the law of multiple proportions. And the law of multiple proportions says that if you've got two elements, right, A and B, and they form more than one compound, the masses of B that combine with a given mass of A are in a ratio of small whole numbers, right? So what that means then is that, for example, small whole numbers ratio means that, for example, if you have something like water, right, which let me make sure I can write this without skipping to the next slide. You have something like water, so water is H2O, right? The ratio of the ratio of hydrogen to oxygen, right, is 2 to 1. Okay, 2 to 1, right? So that's what the law of multiple proportions is, because it says that ratio will always be a small whole number, and here it's 2 to 1, right? What's another good one? We have sodium chloride, right, NaCl, right? So the ratio of sodium to chloride is 1 to 1, right? Again, water, hydrogen to oxygen is 2 to 1. Right? Does that make sense? So that's what the law of multiple proportions says. Okay. You're never gonna get a decimal point number or a fraction for the number the ratio number of atoms in a chemical formula. Okay. You're never gonna see you're never gonna see damn, I can't even think of one because it very rarely ever happens. Anyway, so the guy John Dalton himself actually discovered this one, right, while he was developing the atomic theory. So this one, the law of multiple proportions, is the only one that John Dalton discovered himself and developed himself, right? The law of conservation of mass was discovered by Antoine Lavoisier, right? And then I keep on saying it different every single time. And then the law of constant composition was discovered by Joseph Proust, right? Proust. Okay, so remember, the only one that Dalton came up with himself was this one, the law of multiple proportions. Okay, so the reason why I want you to remember that is because your next question is this: which law is the only law, right, that Dalton discovered himself? Which law is the only law that Dalton discovered himself? Okay, and that was a link I accidentally put in there for you the first time, for the first question. Okay. Which law is the only law that Dalton came up with himself? And let me get the link for you again, just in case. Already got 5 people responded. Good. See, we're on it now, guys. We're on it now. Wingardium Leviosa. It's Leviosa, not Leviosa. Who would have thought that the pronunciation of charms is so nuanced? There's a link for you. That should be the correct link. 7 responses so far. I'm glad to see that most of you have been paying attention. Most of you have been paying attention. We've got 9 people responded already, so I'll go ahead and show the results. Everybody else, the last 4 people, make sure you get your answers in. Okay. And so here is the breakdown. Here is the El Breakdown of the answers, right? Most of you put C, the law of multiple proportions, and that is correct. Dalton himself did come up with the law of multiple proportions. He did not come up with the law of constant composition. That was Joseph Proust. And then the law of conservation of mass was Antoine Lavoisier, right? And then the last one, which is the law of multiple proportions, that's the one that Dalton came up with himself. Okay, good stuff. I think some of you are just waiting for me to reveal the answer for you to do your attendance. That's just wrong. That's just wrong. I'm perfectly fine with it, but it's still wrong. So, all right, let's keep going. So, by the way, that's a picture of Dalton right there. In your textbook, for those of you who don't have a textbook, in your textbook when they talk about these talk about Dalton and the Dalton's atomic law. They have this very like suave picture of him, you know, he's this very suave picture of him, like, you know, in very pensive, thoughtful mood like this, right? Thinking about the Dalton's law. You're thinking to yourself, man, I wish I could be as cool as John Dalton, right? And so there's like this cult following, and there's like memes and stuff like that of all these different pictures of John Dalton thinking, because apparently it's so like, you know, philosophical and so profound in the chemistry world, which you guys probably don't really care right now, but you will soon someday. No, well, actually, most of your biology majors, but if you're a chemistry major, you'll care later on in life, I promise. So there are four of these postulates that Dalton has in his theory of atoms, or his atomic theory. And since the book had such a suave picture of him thinking for these postulates, I myself decided that I was going to, in this presentation here, provide you with the glorious sight of all of these wonderful portraits, different portraits of John Dalton, if you were wondering what he looked like, you know, in his different poses. Okay. I'm driving now, so I will be doing this on my phone for the rest of the lecture. I'm sorry. Oh, because you have lab today, right? Because someone made you go to the lab today. It's fine. Just listen. Just listen to me today, okay? I'm sorry that you guys have to go into the lab today. What was I saying? Oh, the wonderful pictures of John Dalton, right? So yeah, so just, you know, put the phone on the, you know, plug up the phone to your Bluetooth, and hang it on the little you know, phone holder thing, right? You know, in your AC vent, right? And just, you know, listen to me talk while you're driving, and I'll try not to put you to sleep, because that would be very dangerous right now. All right, so the first one of Dalton's atomic theory. The first one of Dalton's atomic theory is this one, and it says that each element is composed of extremely small particles called atoms, which is pretty obvious these days, right? But at the time, you know, John Dalton in his thoughtful pose right there with his, I can't tell, is his finger pointing at his glasses? Is he moving his glasses, or is he just using that to, like, is that just a very pensive look? I don't know, right? He posed for that painting, I think. Anyway, it's pretty obvious, right? All elements are composed of very small things called atoms, right? So here we have an atom of oxygen right here. Oopsies. We have an atom of oxygen right there, and an atom of nitrogen. Okay. Interestingly enough, you're going to have to work with molecular model kits eventually in lab, and the colors are actually matching, right? So you have an atom of oxygen, which I wish I could show you, but they're at school, and I haven't been to campus for like 2 months. So, but when you look at an atom of red, a red atom inside the molecular model kits, the red is always oxygen, and then the blue one is always nitrogen, just like it shows here on this slide. Okay. So the second of the postulates in Dalton's atomic law, right? Atomic theory, is that all atoms of a given element are identical to one another in mass and properties, but atoms of one element are different from atoms of another element, right? Again, a very obvious thing to state, right? But back then they weren't sure. So today we know for a fact that all oxygen atoms, right, are the same, because they are all members of the element oxygen, right? The element oxygen. And then all atoms of nitrogen are the same, right? Because they're all part of the element nitrogen, correct? Right? But the atoms of oxygen are very different from the atoms of nitrogen. They're very different from each other. Okay, so that's a big deal there. And so just to describe the photo we have here now, or the painting we have here now of John Dalton, he's doing his Napoleon pose, right, where he puts his hand into his vest, which I never knew why people did that. Like, I don't have any buttoned shirt on right now, right? But wait, is that his left hand or his right hand? That's his right hand, I think. Yeah, so he puts his in his vest right there. He's like, I'm very pensive and I'm holding onto my heart because my theories come from the heart. Okay, so that's what he's doing right there. He's very thoughtful, that Dalton. Okay. Oh, look, another Dalton picture. I think he's holding a newspaper now. No, that's not newspaper. That's actually pictures of atoms and orbitals. You'll talk about atoms and orbitals later in life, I promise. Maybe even with me, if you take Gen Chem 2 with me. Um, so the third postulate, right? The third postulate of Adams' atomic theory is that atoms of an element are not changed into atoms of a different element by chemical reaction, right? Atoms are neither created nor destroyed in chemical reactions, which you said that in a second ago, right? We said that a second ago from as an extension of uh, Antoine Lavoisier's uh, conservation of mass, right? Law of conservation of mass, right? So you cannot change an oxygen atom into a nitrogen atom using a natural chemical process, right? Using a natural chemical process. And notice I said natural chemical process because you can do it like, synthetic ways, right? Where if you have like, I don't know if anybody has heard of like the CERN super collider, where they're like shooting like particles at different things, like they go really fast in a circle and they hit things. So, if you hit like, a proton into an atom, right, of something, it actually changes the atom's atomic number of the proton sticks, right, because the atomic number is the identity of the atom, and so you could do it that way, but that's not natural, right? It's not natural for you to have like a super collider that's acres in size. It's a big circle, and these particles are just spinning around in a circle. Oh, it's actually, if you ever seen Iron Man 2, right? Have you ever seen Iron Man 2? Anybody? It's probably one of the worst. I mean, not worse than like the Hulk, but in Iron Man 2, um, what's his name? Tony Stark is trying to come up with a new element, right? And Jarvis is helping him come up with a new element, and he builds a little mini super collider, right? Little mini super collider inside of his lab or his garage, right? And I forget what the name of that element was. What was the name of that element? But anyway, he's doing that because he needed something that was less dangerous than palladium or something, because it gives you like heavy metal poisoning. He needed something that was more stable and less dangerous to maintain his arc reactor, right? His arc reactor. But to do that, remember, he had that little mini super collider, and it was going around in circles, right? The particles were going around in circles. It was a little mini super collider, and then eventually it hit something, right, and it created a new element. So let me just tell you though that looks super cool in TV in the movie, right? It's very unreal because for you to have a super collider, we're talking like acres, right? We're like it's got to be huge, like mother huge, right? So anyway, that can't happen in real life. I mean, sorry, that can't happen naturally though. Naturally, if a chemical reaction is occurring naturally, you will not change an atom of oxygen into an atom of nitrogen. Okay, it's only people that want to challenge the natural laws of the universe. Only humans. Okay, why can't we live like dolphins or something? Just swim and be happy. The ocean, swim. Yeah, exactly. All right. Now there's the fourth postulate, right? Oh, I forgot to say that's definitely a picture of John Dalton holding maybe like one of his papers, and he's like, oh, this is just extraordinary. He's thinking to himself, right? This is extraordinary. My thoughts are just extraordinary, and he's looking at these papers here that he's published on the atomic theory, right? Which are still tried and true today, by the way. Okay, tried and true today. So maybe he should get that credit, right? Should get that credit. All right, so here for Dalton's fourth postulate, right? Atoms of more than one element combine to form compounds, right? A given compound always has the same relative number of kinds of atoms. For example, right? We can actually have an atom of nitrogen here, and uh, an atom of oxygen here, and they will combine together, right? These are all elements, right? And they combine together to make a compound. This compound is called nitrogen monoxide, right? Nitrogen monoxide, okay? Nitrogen because there's only one nitrogen, right? And then monoxide because there's only one oxygen, okay? And so that's what the fourth postulate says. And in this particular picture, he's again looking very pensive and thinking to himself, I think I've just discovered what causes. Actually, I need to make sure before I say it because I think I got it wrong last time. Let me look it up real quick. Let's see here. It's not laughing gas, not nitric oxide or nitrous oxide. Let me see. Nitric oxide. Let's see what nitric oxide is. Can I get a picture, please? I just want to see a picture of nitric oxide. Okay, that's nitric oxide. Okay, I was right. Okay, so if you if you didn't know, nitric oxide is actually the thing that causes erections. Okay, it's the compound that causes erections. So, like for example, when a man is taking Viagra, it actually increases the nitric oxide in their blood, right? And that's what causes erections. And so, what I was going to say, and I need to make sure first, right? Because the IUPAC or the normal the systematic name for this compound is nitrogen monoxide, but it's like common name, right? And the name that they use in medicine is actually just nitric oxide, right? Just nitric oxide, one oxygen and one oxygen and one nitrogen, right? And it's known to cause vasodilation in people, right? And it's known to cause vasodilation in people, right? Which primarily is used for erections in people, right? And so when a person is prescribed Viagra or Cialis or any of those other ED medications, right? What it's doing is that it's increasing the nitric oxide in your in the bloodstream, right? And that's what helps them with their little problem that they'll have, right? And so here, Dalton's thinking to himself, "Oh, I've discovered the compound that causes erections," right? So it's great stuff, right? All right, so whew, which postulate of Dalton's atomic theory stated that atoms are neither created nor destroyed by chemical reactions? We just talked about this, okay? Just talked about this. So for those of you who are capable of actually answering this question, feel free to scan the barcode and answer this question, right? Because if you're driving, please don't stop driving or don't try to answer this question while you're driving. That's incredibly dangerous. Oh my God, it's already 12:42. This class goes by so fast. I've only gone through like 4 slides. What is happening here? What is happening?
Time flies when you're having fun.
I think it's me having fun, not really you guys, but me. Oh man, I can't believe this class is almost over. It's only got like 20 minutes left. All right. Let me get the QR code link out for you real quick here. If you need it. There it is. So one person has responded so far. And that one person got it right, I think. Yeah. Pretty sure he did. He or she. Let's see here. Copy, paste in, and there we go. There we go. All right. Wow. It's like completely mixed right now. It's like the same number of people have answered the different answers. Like it's all split. Six people have responded. Good, good, good. You 6 people or 7 people that responded, are you already on campus? Is that why you don't have to drive? Eight people already. Or maybe you're just very close to campus and that's why it's not a big problem. Gotcha, gotcha, gotcha. All right, I'm going to go ahead and show the answers here, right? It was a mixed bag of answers here, but that's okay, right? That's okay. Um, oh, you have to miss lab today, Courtney. I'm sorry. Did you tell Ms. Dickens that? Did you make sure she knew that you were going to miss lab today? That's important. I don't want her to not mark you as not active. Oh, okay. You'll be making up next Friday. That's good. Okay. All right, so Raymond, you got there at 8 a.m. Oh my God, you're more responsible than I am. I teach there and I don't get there until like 10. So that's just unbelievable. You too, Alondra? You got there at 8? Why? Why are you doing this to yourselves? Why are you doing this to yourselves? All right, so 10 people responded, and half of you answered correctly. The answer is indeed C, the third postulate here. I had drill at 5 a.m. and then I headed to there soon thereafter. Oh, okay, that makes sense. If you're already awake, that totally makes sense. But if you weren't awake and you woke up to get to school at 8, wow, that's dedication. That's dedication. So half of you answered C, which is the third postulate, right? Let's just go back and see who's right, right? Let's go back and see who's right. There it is. It's the third postulate. Good job, you 5. I got that one correct, right? Good job. Good job. Okay, so let's keep on trucking along here. Let's keep on trucking along here. So after that, right? After that, we had Dalton. After Dalton came up with his atomic theory, right? The atom was then. Sorry, let me say that again. After Dalton came up with his atomic theory, we all believed that the atom was the smallest particle, right? But it turns out, right, that many discoveries after that led to the fact that the atom itself was actually made up with even smaller particles, right? And most of you know what those are already. Those are neutrons, electrons, and protons, right? And so we're going to talk about this a little bit too, right? How they discovered those things, okay? Also with radioactivity and stuff. Okay, so the electron, right? Here's a nice little picture of the electron. And what you see on the screen here is what we call a cathode ray tube, okay? So electrons are also known as cathode rays, right? And if you see it, you can see in the picture here, right, that the cathode rays, or the electrons, right, they actually emanate, right? They actually emanate from the negative electrode, right, or the cathode over here, right, and go towards the anode, or the positive electrode over here, which makes sense because everybody should know, right, that electrons are negative, right? Electrons are negatively charged, okay? Electrons are negatively charged, and so opposites attract, right? I mean, sometimes opposites don't attract, right? There can be a lot of clashing and a lot of differences in their opinions and their feelings, right? Because that's like the very definition of opposites, right? But sometimes they do attract, okay? And so since opposites attract, you can see in this cathode ray tube, right, that electrons are flowing from there to there, right, towards the anode, okay? And the other interesting thing too is that when you have a magnet right here and you bring it towards the cathode ray tube, you can see that the cathode rays inside the tube start to bend, right? Crazy stuff, crazy stuff. And so that's why we now know that's how they were able to actually discover or come up with the fact that that electrons, electricity, and magnetism are actually very closely related to each other, right? And we'll talk more about that later, but that's what it's coming from, right? So streams of negatively charged particles. These are the cathode rays or the electrons, right? Were found to emanate from cathode tubes, causing fluorescence. They actually glow too. Cool stuff. This guy discovered this, J.J. Thomson, right? Not to be confused with J.J. Watt, but J.J. Thomson, right? Which is actually kind of funny because J.J. Watt would have been more appropriate because, his name is Watt, and Watt is a unit of power, right? Like, milliwatts, kilowatts, kilowatt hours. That being said, watch your kilowatt hours over the next few days. You don't want to get your power shut down because you're using too much heat, okay? So J.J. Thomas / Watt here, I'm just kidding, just as J.J. Thomas, is credited with the discovery of this in 1897. Good stuff, good stuff. So let's talk about the electron then. Let's talk about the electron, right? Thomas measured the electron's charge to mass, right, ratio, right, which is just C for charge to mass ratio, right? That's basically the electron's charge divided by its mass, right? And he found it to be 1.76 times 10 to the 8 coulomb grams, right? And that doesn't mean too much to you right now, right? But it will later. It will later. I'll tell you why in a little bit. Okay, so here's another cathode tube here, right? And you can see the electrons right here, right? Here are here's the negative cathode right here, and electrons are flowing towards the anode there, right? It goes past the anode and it hits the fluorescent screen, and now you can see a uh, fluorescence, green fluorescence. Pretty neato mosquito is what I say. Pretty neato mosquito. Okay, so this is an even better experiment. I think this is even cooler, right? So here's this guy named Millikan, right? And Millikan did this thing called the oil drop experiment, right? Uh, and he did this so that he could figure out what the charge of electrons were, okay? And we, like I said, most people knew already, or at least thought already, that electrons were negatively charged, right? But this really did it. This really did it. So once the charge to mass ratio of the electron was known, right, determination of the charge or the mass of electron would yield the other, right? So what that means is that if you had the charge to mass ratio, right, then you could use one of those to figure out the other, right? So if you had the charge, you can figure out the mass. If you had the mass, you can figure out the charge, right? So what Millikan did in 1909, right, he determined the charge on the electrons. And this is a cool experiment here, okay? Inside this chamber here, right, he had at the very top of the chamber right here, right, oil being sprayed, right, into the top of the upper chamber, right? And there's this hot plate here, okay? So it's heating up the oil, basically, okay? It's heating up the particles of oil, okay? It's heating up the particles of oil. And then you have the top part right here charged positive, and the bottom part of the chamber charged negative, right? And then what he did was he shot X-rays in there, right? He shot X-rays in there. Okay, he shot X-rays in there as there's a little hole right here, right? And the oil particles start to fall down to the second chamber, right? And the reason why the oil particles fall to the second chamber is because of gravity, right? Gravity pulls oil, it drops the oil downward, right? But the funny thing about that is that the things that were negatively charged, right, would actually go up towards the positive plate, right? Up towards the positive plate. And so that's how you knew that electrons were negative, right? Because what happens is that the oil droplets were actually neutrally charged when they went into the second chamber, but then when you shot the X-rays at them, right, it made them a charge, right? You didn't know what charge it made them, but it made them charge, right? Because the X-rays were shooting electrons basically, and you didn't know what the charge was, and so when they shot the electrons or they shot X-rays into the oil, which are the electrons, it made the oil bind to the electrons, right? Pick up an electron, and those oil drops that actually gained an electron, right, from the X-rays became negative. And since they became negative, they actually were now attracted so strongly to the top part of the plate, right, because it was positive, that they overcame gravity, right, and started going towards the top plate instead of going down to the ground, right, or down to the bottom plate with gravity, right? But it also makes sense too because since the electrons are negatively charged, not only would they be attracted to the top plate because the top plate is positive, they're also being repelled from the bottom plate because the particles of the same charge repel each other, right? And so since the bottom is a negative, right, it's going to repel those electrons. So that's two things, right? The electron that is being held onto by the oil, right, is not only being attracted to the top plate in the Millikan experiment because the top plate is positive, but it's also being repelled by the bottom plate, pushing it up to the top plate, right? So using that experiment, we figured out then that electrons are actually negatively charged. Cool stuff. I want to try this at home sometime. Would that be safe though, having X-rays in your house? Probably not. Anyway, so in this experiment, the Millikan experiment, what type of electromagnetic radiation was used to determine the charge of an electron? And I'm not going to make you answer that because I didn't change. I did not change the the answers to reflect what answers I wanted to be there. But I'll go ahead and tell you. I was going to say UV rays, UV. I was going to say IR. I was going to say gamma rays. And then I was going to say X-rays. See, this is what I call like creating a PowerPoint during the lecture. It's awesome. X-rays, right? Okay, X-rays. There we go. And then we'll open that back up again. There we go. So go ahead now. Scan that QR code and answer the question if you can. And I will put a link in there for you if you need to see the link. Okay, you know what? I really screwed the pooch on this one, because I think that QR code sends you to a different thing. Let me scan it myself and see. Hold on. Oh my God, seriously? I was just logged in. Why are you making me do this again? Why are you making me do this again? What is this business? What is this business? Oh my God, how many times? How many questions I have to answer? Yeah, I apologize. I screwed the pooch on that one. You don't have to answer this question because I didn't even have a barcode, a QR code for this question. But the answer for this is X-rays, of course. Okay. So, Jakir, I think that was Jakir that asked me to put the link. There is no link, so forget it. Let's just keep going forward. All right. See, this is why you love this class. It's so flawed. Right? It's so flawed. Okay. Oh man. Dang, we only got like 10 minutes left in class. 15 maybe. All right, so let's talk about radioactivity right now. To the right, you see a picture of Marie Curie, right? Marie Curie. And Marie Curie, right? She was actually, her and her husband discovered the atom, not the atom, the element radon, by the way. And so I don't know if you remember this back in the day, but during the war, like during World War II, and even maybe in World War One, I can't remember the exact year or which war it was, right? But what was super popular back then was these watches that had like glow in the dark like dials, right? So you could be in the dark and you could read your watch, right, to see what time it was. Which is good because if you're in war and you're in like a battle or something, the glow was just bright enough that you could see if you're looking at it, but it wasn't bright enough that it would give away your position to the enemy, right? So the way they actually made those watches glow was in watch factories that were using radon, right? And so they would have girls come in, like young girls too. Like this is around the time before they had like child labor laws and stuff like that. So they had young girls and women too go into these factories, and they would actually go through and hand paint the faces, these watch dials, right, with radon paint that glowed, right. But the thing that was really crazy about it was that the radon was actually radioactive, okay. And so, but they didn't know at the time that radon was radioactive, right? Or maybe they did. I'm not sure. But these women, right, would actually, dip their little paintbrushes into the little jars of radon, right, and then paint, and then to clean off the brush, they would lick the paintbrush, right, and then they would dip again, and they would go through all day painting watch dials with radon, right, so that the tick marks in the watch dials would glow in the dark. And all day they were just dipping into the little thing of radon, licking it, making it wet, dipping, licking, blah, blah, back and forth, right? And then to say nothing of the fact that during break times, everybody thought that radon was safe. That is it radon or radium? I can't remember now. I have to look. They sound so the same. Let me look it up real quick. See, this is why we have Google. Radon. Oh, my bad. Okay, good thing I checked on that. It's actually not radon, it's radium. Okay. And so radium, right? So these girls were going back and forth, and they were licking their paintbrushes, and they were licking their paintbrushes, and then putting them into the little paint jar of radium paint, and then they would paint the dials, and then they would go back and forth all day. Just that's how they did it. And so what happens then is that they actually go and during break time, which is even worse, and during break time, people didn't think that radium was dangerous, and so these girls would go on and paint on their lips to make their lips glow. They would paint the radon on their eyes to make it look like eyeshadow and make their eyes glow, and on their like eyelashes and stuff like that. And so, what was crazy about that was that years later, right, these girls would start succumbing to their radiation poisoning, right, and their jaws would start falling off, their bones started deteriorating. It was just a really bad situation. Okay, and nobody knew why at the time. Nobody knew why these girls were dying. These women who seemed young and healthy at the time suddenly succumbed to this disease where their bones were deteriorating, especially in their face and their head were deteriorating, right? And their faces and their skulls were just falling apart. Okay, so these people ended up dying, right? And a lot of them, these women that were in these factories ended up dying, and nobody thought anything of it because they didn't know what was going on. Well, years later, a forensic scientist named an ME actually, a medical examiner named Charles Norris, not to be confused with Chuck Norris, Charles Norris. he and his forensic scientist Alexander Gertler, right, were hired, or not hired, but were tasked with trying to figure out what killed these women. And years later, right after these women had already died, they had taken these the bones. They exhumed the bodies and took the bones of these women who had been exposed to radium, and they put it onto the special paper, the special photo paper, right, that would actually interact with radiation, and it would leave big spots where radiation was coming out, right? And so they would take the bones, put it into on top of the paper, cover the paper, and come back like the next day. And they came back like the next day, took the bones off the paper, there were literally black or dark spots, exactly in the shape of the bones from these women, right, on the paper that were made from the radiation on the paper. And so his phrase was, all these years later, and the radium still glows, right? And that's what ended up killing those women. So stay away from radium. It's bad for you, right? It glows in the dark, but it's crazy. Okay. So I tell you that because Marie Curie and Pierre Curie actually discovered radium and a whole bunch of other things too, and they actually both of them end up dying of radiation as well later on in their lives. I actually had the pleasure and the honor of going to the what's called the Pantheon, and it's in France, right, in Paris, and their bodies are buried in the Pantheon in Paris. In Paris, it's a huge memorial place for them, right? So it was pretty cool. So be careful of radioactivity. What is radioactivity? It is the spontaneous emission of high energy radiation by an atom, which makes sense, right? Because this radiation from the radium, for example, was like the high energy was so high, right? It was changing the DNA that was in the jaws and the faces of these women, right? And you'll learn a lot more about that later too, about how electromagnetic radiation. Not all electromagnetic radiation is dangerous, but radiation is, right? Like X-rays and gamma rays and stuff like that. And it changed the DNA that they had and the proteins they had in their jaws and their bones so much that their faces were falling apart. Their skulls fell apart. It's quite crazy, right? Quite crazy. Okay. So yes, its discovery showed that the atom was more than just subatomic particles. They actually had energy associated with it. Okay. Energy associated with it. All right. So then you have radioactivity. Oh, sorry. Then you have Rutherford, right? And Rutherford was a cool guy too. Okay. And he actually discovered three types of radiation, three types of different radiations, right? He discovered the alpha particle, right, which is right there. They're positively charged, okay? Positively charged like protons, right? And then there's the beta particles, which are negatively charged, like electrons, right? So not exactly like protons, not exactly like electrons, right? But they are charged like them, right? And they also have the gamma rays, right? And the gamma rays are they're some terrible stuff, right? Well, I guess the gamma rays are good because they created the Hulk, right? The Hulk was created with gamma rays. But anybody else, I mean, I guess exposed with gamma rays would die, right? And so let me actually move my face out the way here so you can see what that says, right? So he had here in his experiment, right, a lead block, right? And inside that lead block was a source of radiation, right? Some kind of radioactive substance. And of course, have you seen people working at like nuclear power plants before? They all wear lead suits everywhere because they don't want to get like, exposed to radiation. So that's why he used the lead block here. And so what happens is that the lead block had a hole at the end, right, where he could direct the source of radiation out through that hole, right? It goes through this little filter here, and then it encounters these electrically charged plates, negative and positive, right? And when that happened, when it goes through that, you could see that the particles that were positively charged, right, which were the alpha particles, came down here because they were attracted to the negative plate, right? And then the beta particles that were negatively charged went up here when it shot out, right, because it was attracted to the positive plate, right? Also repelled by the negative plate. But then the gamma rays that were uncharged went straight through the middle. Okay, they were unaffected by those changes. Okay, unaffected by those changes. And so that's how Rutherford was able to discover, right, that there were actually three types of radiation, right? These three types: alpha, beta, and gamma rays. Alpha particles, beta particles, and gamma rays. Bad stuff. Bad stuff. Well, alpha particles, beta particles, not so much, but gamma rays, bad stuff, right? So then, right, there was this other guy that you already met before, J.J. Thomas, right? Not to be confused with J.J. Abram. Wow, so many people named J.J. J.J. Thomas, J.J. Abram, J.J. Watt. I wonder if there are any other J.J. Anyway. So he came up with this thing called the plum pudding theory, all right? Which us here in the South, I've never even heard of plum pudding. I don't even know what plum pudding is. Anyone know what plum pudding is? I actually like to call it the chocolate chip cookie theory. Chocolate chip cookie. Uh-oh, don't know how to spell cookie. My heart of Asian again, or heart of English. I can do it. Don't tell me how to spell cookie. There we go. The chocolate chip cookie theory, okay? And what he said was that an atom, right? What J.J. Thomas here said was that an atom, right, was actually negative electrons, right, that were floating randomly about, right, in a sphere of positive charge, right? So the sphere was all positive, right? The entire sphere was positive charge, and then the little dots on the inside were spread randomly inside the sphere, right? Inside the sphere was the negatively charged electrons. Okay, that's what he thought it was, right? And again, I don't know what plum pudding is, but think of it as a chocolate chip. If you look at a chocolate chip, right, the cookie dough part of the chocolate chip would be the positive part of the atom, right? And then the chocolate chips themselves would be the electrons. That's the chocolate chip theory. That's what I like to call it, right? But I guess if you don't like chocolate chip, you could say like raisin oatmeal cookie theory. Anything that has, that kind of thing. Anyway, so let me just tell you that J.J. Thomas was wrong. Okay? J.J. Thomas was definitely wrong about this. Because Rutherford, again, comes in, right, and discovers the nucleus of the atom. And the way he discovered the nucleus of an atom is because he used alpha particles. And if you remember back in the previous slide here, alpha particles are what? They're positively charged. Okay? And so in his experiment, right, he shot alpha particles, the positively charged particles, at a thin sheet of gold, and then observed the patterns of the scatter, like when the alpha particles went into hit the sheet of gold, they scattered, right? And he observed the patterns, and then he noticed, right? He noticed that whenever an alpha particle hit an atom of gold, it actually gets deflected when it hits the center, right? It hits the center, it gets deflected. But it doesn't get deflected, right? If it doesn't hit the center, it just goes right past if it doesn't hit the center of an atom. So what that meant was that the center of the atom was positively charged because it was repelling the positively charged alpha particles, right? And nowhere else in the atom was doing that. And the gold atoms was doing that. And so that's why, oh, J.J. Jameson. Thank you, Raymond. Anyway, since the alpha particles, when they entered the center of a gold atom and got deflected, right, you can surmise from that the center of the atom, right, that the center of the atom was positively charged because the positive particles will actually repel each other, right? The one coming from the alpha particle and then the positive charge inside inside the nucleus, right? And then when it didn't go through the center but went around it, right? You knew that there were no other particles that were positive anywhere else in the atom but the center, right? Because they didn't get deflected, right? And so from that, Rutherford discovered the nucleus of an atom, right? Rutherford discovered the nucleus of an atom, right? Using alpha particles. And so now everybody knows, right, that the atom is composed of a nucleus that has neutrons and protons in the center, right? And then it has electrons that are in clouds, electron clouds or energy levels around the nucleus. Okay, good stuff. So this will be oh, here we go. This is actually a closer picture of the nuclear of the experiment, right? See, I do this. I told you guys I did this last time. I always jump ahead and tell you things before it's actually in the slides, right? Thomas was wrong. He was so wrong. Okay, because incoming alpha particles, right, go straight through on the sides of these atoms, right? But when it hits the center of an atom, it gets deflected. So there had to be something positive only in the center of the atom, which we can call that a nucleus now. Okay. And so here, just a little bit more, some stuff about the sizes and stuff, the relative sizes, right? Rutherford postulated that a very small, very dense positive center of electrons. Sorry, let me say that again. Rutherford postulated that there was a very small, dense positive center with electrons that are around the outside, right? Which I told you that just a second ago, right? The most dense atom, this is a big thing too. Most of an atom is space, right? So even if you're talking about my Apple Pencil right here, right, which is made of plastic, right? Probably polycarbonate plastic, which has also electrons, right? But if you didn't know, most of this is actually space, right? And it's the space between the electrons and the nucleus, right? That's crazy, okay? Atoms are very small. They're only 1 to 5 angstroms, which is 100 to 500 picometers. That's super, super small, right? That's a larger decimal. It's a decimal with how many zeros? I can't even remember now. I should know what pico is, but I just can't remember. I get on these rolls and then talking to you guys about chemistry, and it's so much fun, and then I don't even remember what pico means. Picometer. So 1 picometer, right, or a pico is 1 trillionth of a meter. Wow, 1 trillionth, right? So that's not 1,000th of a meter. That's not 1 millionth of a meter. Not 1 billionth of a meter, right? But 1 trillionth of a meter, right? So millionth would be 6 zeros between the decimal point and the number, right? And then millionth would be 9, right? And then trillionth would be 12. So 12 zeros right there. That's a really, really small number, okay? And then other atomic subatomic particles and protons and neutrons are discovered, nucleus are discovered. We already said that before. And so here's just a picture just describing what I just said on the side there. So this is actually your last question for today, and it ends our class, right? And if you can answer it, go ahead and answer it. Scan the QR code. In Rutherford's experiment, what type of particles were used to discover the existence of the nucleus of an atom? Right? What type of particles were used to discover the existence of the nucleus of an atom? And I will see how people are answering that question. Oh, someone's coming onto the microphone. Who is it? It's Terrence. Terrence, you sound like you're driving. I don't know if Terrence can hear me. Terrence, if you can hear me, I'm going to put you. Oh, you did it. Thank you. So one person's answered. 2 people have answered. Three people have answered. Oh, the link. I'm sorry. I totally forgot. Ah, man. Sure, totally forgot about the link. Thank you, Courtney. All right, I'll give everybody a few more couple chances to answer the question before I reveal the answer. Man, wasn't today's lecture awesome? I mean, it was about atoms and molecules and erections, basically, right? That crazy, Dalton. You know, Autumn. There's Autumn. You know, there's an elevator. By the way, you know, there's an elevator to go upstairs. Just saying, there's an elevator. Like at the back of the building, there's an elevator. So, and you can be for damn sure that I'm using the elevator. Like I always use the elevator. And for some reason, the stairs in that building, like they're very steep. They feel steep to me, so I'm always using the elevator. Anyway, just as a recap to what we talked about today, we talked about atoms, atomic theory, nucleuses, and erections. Okay, it's crazy stuff, right? All right, I think enough people have answered. So here is the breakdown right here. Whoops, what happened? Whatever. Here's the breakdown right here, right? And most of you got that one correct. The answer. Wait, hold on a second. Where's it at? That's the wrong question. There it is. Most of you got the answer correct because the answer is indeed alpha particles is what was used. And some of you answered gamma rays. He did use gamma rays right here, right? He used gamma rays right here, and he used gamma rays to discover the 3 different types of. Well, he didn't use gamma rays, but he discovered gamma rays here, right? When he discovered the 3 types of radiation. So that there was something that gamma rays had to do with Rutherford. So good on you for remembering that. But the actual answer is that he used alpha particles. All right, he used alpha particles. See, alpha particles. All right.